Well, I'll say good morning to everyone. So I wasn't here on Tuesday because I had a meeting in Chicago. So as I'm flying to Chicago, they canceled my meeting. So I get to Chicago, there's no meeting. Spent a little time at the airport and flew home. So kind of a wasted day, but anyway. Yesterday was a big day. What was yesterday? What? I missed Halloween? Oh, Halloween, yeah. Forgot about that. We had a basketball game. That's what it was. I didn't see any of you there last night. I was looking, but anyway. So the last lecture, we talked a lot about what I'll call the Scatterplate Interferometer, which is a, you can probably guess from my lecture, it was I find it very exciting, very interesting. Very neat device. So I have one more slide on not the scatterplate interferometer, but a scatterplate interferometer. This one is not nearly as useful as the one we talked about last class, but it's really cool. It is so much fun to play with. And for this one, the scatterplate is truly just a piece of ground glass. And you want one that doesn't scatter 100% of the light, but scatters large amount of light. And that's the only requirement. In fact, I've never found a piece of ground glass that didn't work as the scatter plate in this interferometer. So we start off here with a source, and again, it can be any source. And again, a lens. It doesn't have to be much of any lens. And I lost my pointer here. Beam splitter, piece of ground glass. The mirror we're testing. So this scatter plate is near the center curvature of this mirror. The light from here is imaged onto a flat mirror, which is back about the same plane as the scatter plate. And the light goes back here to the mirror and back to the scatter plate. And back here we have an interferogram. So we it's very, very simple to set up. It's almost nothing you can do wrong in setting this up. And now if I say move either the scatter plate or I move this mirror, well, I should say this mirror here is imaging this scatter plate, ground glass, onto this mirror, or close to that anyway. And if I move either the scatter plate back and forth or the mirror back and forth, I'll see my circular fringes that I normally see. And it can be, it can be a white light source. That's no problem. It doesn't have to be a real small source. You can actually move a source around and nothing much happens. You can move this lens back and forth and nothing much happens. The major effect is either moving the mirror back and forth or moving scatter plate or this mirror here back and forth will change the number of fringes you have. Now this is very fun to set up. It's very cool. It's fun to play with, but it's not very useful. And there's one thing that's wrong with it, and I want you to tell me what is wrong with this. Why is this not a good way for testing this mirror? I mean, it's very cool to play with. When I teach the lab for this course, this is part of one experiment. We have the scatter plate, the interferometer we talked about before, and then we have this for the same experiment. And this one is simpler than the other one, and that scatter plate is just a piece of ground glass, but it's not nearly as useful as the other one. Is it insensitive to vibration? Yeah, pretty much so. I mean, it's a common path. Both interfering beams go here. Again, it's the scattered direct and direct scattered that gives you the fringes. But what is wrong with this? Yes?
Does that have to do with how light has to come in an angle to the mirror surface?
Yeah, typically you don't like to do that, but the angle is small, and compared to the real problem, that's a minor problem. How would I introduce tilt in this instrument? Can I just tilt the mirror? What's that? Yeah.
You'd have to tilt the scatter plate on the mirror.
Well, yeah, I won't. It's minor. It's minor. Let me think. Let's just trace a ray here. You know, some light goes here and it goes up there, and that's going to image it down here, and going to come down here and back. Well, the beam when it goes back here is flipped over. Up here, up here. And so if I try to tip and tilt this, because of the double pass off of it, I don't see a change in the OPD. So I can't introduce tilt fringes. But the real problem is the beam is flipped over here, and so I don't see the odd aberrations. So if I'm just measuring something for spherical aberration, I guess it would work okay. And it certainly is cool to play with, but you're missing the odd aberrations. Okay? Do you believe that? Anyway, this is described as an old article. Some reason I had not seen it until fairly recently, and Malakara pointed it out to me one time when I was visiting him. So I came home and set it up, and I mean it's so easy to set up and so fun to play with, but not nearly as useful as the Scatterplate Interferometer we talked about in the last class. Okay, so that's the end of the Scatterplate. Although I could talk for days on it. I love it so much. But I'll go to another interferometer that I like, and it's what I refer to as a Smartt point diffraction interferometer. Some people don't use the word Smartt. That's Smartt with two T's because it's named after Ray Smartt, who I had gone to school with. And he invented this, but he wasn't the first one to invent it. And I know Linux had invented it before, and probably a few other people had invented it over the years. But it's really cool too. It's what has to be called the world's simplest interferometer. And so, have any of you used the PDI? No? Okay. I mean, I have some optical system here, and I don't care what the optical system is, but it's bringing the light to focus here in some plane here. And in this plane, what we have is a plate with a coating on it that maybe transmits 1% to 1/10 of the light. We'll worry a little bit about that in a minute. But it transmits a little bit of light, not too much. And in the middle of that coating, or someplace in that coating, I have a little pinhole. And the light will come down here, and if this pinhole is small enough, the light that strikes this, there will be a spherical wave that will be diffracted from this pinhole. And if the pinhole is small enough, it will be a very, very clean spherical wave. And so that's going to be our reference. And the light that just transmits through the plate here will be our test. Because the only thing that happens, the light that's transmitted through here will be attenuated because this transmits, 1/10 of the light maybe. But the wavefront will not really be changed. And so whatever aberrations here we're going to have in the beam that's transmitted through here, and the light that goes through the pinhole will be cleaned up, and that will be a nice spherical wave. And these two beams will interfere to give us an interferogram. And it's basically the same interferogram as what we would get if we had a Twyman Green or Fizeau or whatever. And so this is good for testing any optical system here that brings the light to focus. Now, so thinking about this pinhole and how small it has to be and so on, we can think of, whatever wavefront we have back here is brought to focus, so it's like a Fourier transform of that. And we're multiplying that Fourier transform times a small aperture function, round disk, round aperture. And so if I were to re-Fourier transform that again, what I would have would be the aberrated wavefront convolved with a Fourier transform of whatever this aperture is. And so we're convolving whatever wavefront, for the reference beam, we're convolving whatever wavefront we have with, I don't know, what we used to call a sombrero function when Gaskell taught Fourier optics. I don't know if they still call it sombrero function or not, but you have your Bessel function here, and you're convolving that. And I'm not showing the equations here, but I do. One of the references on the web page is called IR, for infrared, PDI. And it's a paper we published a number of years ago. And in that, we go through the math for this convolution process. And it turns out that if this pinhole here is on the order of half an area disk diameter or smaller, almost regardless what aberrated wavefront you have here, you're going to get a nice spherical wave to within, well, at least 1/100th of a wave or so. It really does, it does a great job of cleaning it up. Now, if you make the pinhole smaller, I mean, you're convolving it with a wider sombrero function, you clean it up even more, but then you're getting less light through the pinhole. And I said I wanted to coat this to a transmission of 1/10 of a percent to 1/100th of a percent or so. And that's because I want to have the intensities of these two interfering beams be about the same. And so if I make the pinhole smaller, then I want the transmission of this plate here to be even less. Okay. So generally, something like a half area disk diameter is a good number here. And it's not real critical. I'll come back in a little bit to how we might make one of these. But if we think here for a second, so here's my system that I'm testing now anyways, just a beam coming to focus here. And whatever goes through the pinhole will be my reference, and what's transmitted through here will be the test. If I think for a second, if I move this plate sideways, so that's moving the pinhole sideways. And the beam that just goes through here, maybe the amount of light that goes through might change a little bit or something, but the beam that goes through here will not be changed, but I'm moving the reference source sideways. So that's like introducing tilt between the two interfering beams. Okay. And if you go through the math, again, if you look at that paper called the IR PDI, we go through the math and showing that moving this sideways does indeed give you your. If you move this back and forth, I think, well, the beam that just goes through here, just goes through, but the source of this point spherical wave, that's the reference beam, is going to move back and forth, and so that's going to be like introducing defocus. Okay. So that would be introducing defocus. And so I can simply, by moving this PDI plate around, I can change the amount of tilt, and I can change the amount of curvature in the reference, i.e. change the defocus. So it's pretty simple to do. So you just take this little plate, you mount it on an XYZ stage, and you can move it around. Now, there is one bad thing that happens when I introduce tilt. And can anyone figure out here what bad thing might happen as I introduce tilt? What's that? Right, the amount of light, I think is what you say. The amount of light that goes through that pinhole is going to change as I move it around. If I put it where the light's focused, I'll get a lot of light through. But if I move it out here into the, farther away from the focus, I'm going to get less light going through the pinhole. And so the amount of light in the reference beam will change. And so my fringe contrast will drop off. And this shows that you know, this is without tilt. Now as I move a pinhole sideways, I'm increasing the tilt, but I'm getting less light through the pinhole, so my reference beam, amount of light in the reference beam will drop off, and so the fringe contrast drops away. Now I could have made this PDI, Smartt point diffraction interferometer, to give me good contrast here, say, simply by reducing the transmission of the plate, and so that would have reduced amount of light in the test beam, and so I'd get good contrast fringes here, but then I'd have bad contrast fringes back here. And so you can make the plate for whatever amount of tilt you want, but once you've made the plate, it is what it is. Okay. So it's that kind of limits the usefulness of this. But it's still, it's still a pretty useful little device. I mean, certainly this amount of tilt, the fringe contrast has dropped, but it's still okay. So if I gave you the job of making one of these, how might you make it? And I'll tell you how I made my very first one. I used to be on the 5th floor here a long time ago, and there were thin films people right across the hall. And they were always complaining that the coatings they made had pinholes in the coatings. And so I went to them. I said, well, you have some of these coatings you don't like because of pinholes? And they opened up the cabinet, and it was about filled with these substrates with these coatings with pinholes. So I said, ask them if they'd give me a few. So they gave me a few. And I looked at them under a microscope, and I picked out some of these coated plates where you'd have a pinhole, and then you wouldn't have another pinhole very close by. I wanted an isolated pinhole. And I just set that up in the lab, just mounted on XYZ stage and set it up here. Lo and behold, I had my PDI. Very, very simple. Then we decided we wanted to make a little more, well, we had a little more control over them, and had a student very interested in that. So we decided to make some. And so first off, we had to start with something for a substrate here. And I'll tell you, when I was about 30 years old, I bought 1 kilogram of mica. And I have to say, when I ordered this kilogram of mica, I didn't realize how much mica you get in 1 kilogram, but you get more than a lifetime supply of mica. So if anyone here, if you ever need any mica, come by. I still have a lot of mica left. But anyway, I said, well, let's use mica for the substrate here. And it's birefringent, but it doesn't matter. And then I had a student who went to, he used to make model airplanes, and I guess in the cement he used to glue these together, you put in little glass beads that you could buy at a hobby store. And so he bought a can of these little glass beads for us, so we had, 1 billion, or billions maybe, another lifetime supply of glass beads. And so I had a student who would just take the mica, and he put a glass bead down on it, and then he would coat it. And he always, when you coat it, you turn it over, but the glass bead doesn't fall off. It stays on. They coat it to, the transmission of 1/10 of a percent or 100th of a percent, and then just blow the glass bead off, and now you have your PDI. So they're actually pretty easy to make. So I mean, this, I probably don't even need this particular figure here, but just showing that, all you have to have, whatever you're testing, you just want to set it up some way so it's imaging the source. Small source, has to be a small source. And you're imaging the source, and wherever you image the source, you put the PDI. Now the Ray Smartt, who as I said, was one of the many inventors over the years, and who was a graduate student with me. This is some pictures that he took using one of his PDIs. And this was of a telescope. And what did he use for a star? Well, this one, I guess he used a laser. But for this one over here, he just used as a source, he used a laser. Here he used a star as a laser. And so Ray ended up getting a PhD in astronomy, and he tested a lot of telescopes throughout the world using the PDI. And it worked pretty well. Although I know he got a lot of people mad at him because a lot of people found out the telescopes were not nearly as good as they thought they were. And when doing this test, I mean, you have atmospheric turbulence too that messes you up a little bit. And so you typically would have to take a lot of interferograms and average the results to get rid of the turbulence. Or you can kind of watch the turbulence because the fringes move around, and you could take your exposure when the fringes look the best. And still, you'd like to average a lot. So any questions on the PDI? Well, I think one of the goals of my life was to phase shift everything. And so how do we phase shift a PDI? Well, I've thought a lot about that. And so we have a few techniques we're going to talk about here. And kind of broken into, well, two basic techniques anyway. A little more complicated than this, but using diffraction gratings and using polarization techniques, but some other techniques as well. So one that I kind of liked here, and this one, I remember we had this person, Boker, from Lawrence Livermore lab, came here a few years ago and gave a talk. And this is one of the slides from his talk. So I liked it so much I asked him to send me a copy of the slide. And so what they were doing at Livermore, I mean, here is just our normal PDI of whatever they're testing here, and something partially transmitting coating with a pinhole in it. And that's our, well, we don't see much here in the interferogram, but anyway, that's our normal PDI. So what they did, they modified it. They said, well, let's put a diffraction grating in this beam here. And now it's going through the system under test. And so now if we look down at the focus, we're going to have a zero order, and we're going to have a first order. And one of these will put a very small pinhole to produce our reference spherical wave. And the other one is just an opening. So this is not quite the Smartt interferometer we talked about. It's sort of, well, I say a modified Smartt interferometer. So we just have a large opening here, which might, I would put an attenuation in it because we want to cut down on the amount of light. And some distance away, we have a pinhole. And we have the zero order and the first order here. And back here, we're going to have interferograms. Now, there's a separation between the zero and the first. And so we're going to have a lot of tilt fringes here. Okay. So how would we do this for phase shifting? Well, there's at least a couple of ways of doing it. I mean, if we think here for a second, this grating, if I move this sideways, how is that going to change the orders? Are the orders going to move? No. Are the orders, how will the orders change? Anything about the orders that will change? I know you know the answer to this. No, it won't tilt. It will. You're getting close, though, some way. Fourier optics, shift theorem, phase, right. So if we move this grating sideways, we're going to change the phase of the different orders. And if you go through the math, if I move this one period, well, the zero order is not going to change. And the first order will change. If I move this one period, the phase of the first order will change by 360 degrees. If I move it a quarter of a period, phase of the first order will change by 90 degrees. And so I can do phase shifting here simply by moving this grating sideways. And I'll get a shift of the fringes here. So that's one way of doing the phase shifting. The other way, remember we said that there was this technique where we would have tilt fringes. And if the tilt fringes were such that we had between consecutive elements here, we go a quarter of a fringe, and we could use 4 elements from our detector arrays to get our 4 phase-shifted frames. So if I'm clever at picking this spatial frequency of this grating here, I could use that approach for phase shifting, where I just from one detector element to the next, the phase will change by 90 degrees, and I use 4 detector elements to get my 4 phase-shifted frames. Okay. Does this have to be monochromatic light? Well, it's going to turn out no. But let's think what happens. If I change the wavelength of the light, if I go to larger wavelength, longer wavelength, I go to longer wavelength, does the separation between the zero order and the first order, how does that change? Longer wavelength, the separation becomes, larger separation, okay. But when I go here to the tilt fringes, if I had only tilt, larger separation here, but larger wavelength, it's going to cancel out. And so just tilt fringes here, the spacing of the fringes here is going to be independent of wavelength. I mean, it's great the way this works. I get larger separation here for longer wavelength, but to get a constant fringe spacing here, I have to have larger separation here for longer wavelength. And so everything just works out. So if I have white light here, if I have only tilt fringes, I have to worry about the chromatic aberration of the lens here. If I forget about that, if I don't have chromatic aberration. As I change the wavelength here, the separation here will change in just such a way that I'm going to get constant separation back here. Everything works out very nicely. Now, if I'm going to change the wavelength, or if I'm going to use a broadband wavelength, I have a pinhole there, and I have a large aperture over here. Should I have the first order coming to where the pinhole is, or should I have the zero order where the pinhole is? Zero, right, because you don't want it to move. You change the wavelength, you don't want it to move. And so you want to have the zero order coming to focus where the pinhole is. And then the first order can move around, but you have a window over here, so it still gets through. Anyway, I thought this, I've never used this technique, but it's kind of interesting technique. It's not quite the Smartt interferometer, but very similar to it. Kind of interesting. Another way to do phase shifting, and I like this one because it was invented by a former student of mine, Osik Kwan. And when Osik was a student of mine, he did a lot of work in infrared for his PhD, and he made a PDI for the infrared was one thing that he did. In fact, that paper IR PDI that I mentioned earlier, he was the major author of that paper. So when he left here, he went to work for Lockheed, and this is an idea he came up with at Lockheed. He said, let's do the PDI the following. Let's have a sinusoidal grating on this plate. So this represents our sinusoidal grating. And then here, this little pinhole is the pinhole for the PDI. And he said, well, you know, this grating here is going to produce different orders. So I'll show the 0 order, +1, and -1. And we know that if this grating is moved sideways, we change the relative phase of these different orders. Then he said, well, let's put a little pinhole in here. Okay, so we'll put a little pinhole right there. And so the light that strikes that is going to produce a nice big diffracted beam out here. And a small enough pinhole, it's going to diffract over a large angle. So again, that's our reference. And if we think here for a second, if I'm clever about where I put that pinhole, I can have a 90-degree phase shift between the 0 and the +1, and a -90-degree phase shift between the 0 and the -1. I thought this was pretty clever, Osik myself. And so I'm going to get 3 interferograms here, from, you know, the 0 order interfering with this spherical wave coming from the pinhole, and a +1 and a -1. And these 3 interferograms will have there's a phase difference between them, depending on the position of this pinhole. And if I pick just the right location for the pinhole, I can get a 90-degree phase shift between the two. Okay. I thought that was pretty clever. And he made some of these at Lockheed and seemed to work pretty well. Well, for years, I was dreaming of the following. Let's say we make our PDI in a half-wave plate. Okay? And so I have a hole in my half-wave plate. And the light comes in here. Let's say, you know, I'm showing the S and the P components here. The light comes in here, and what goes through the reference? It doesn't see the half-wave plate, so you know, nothing happens to it, really. It's diffracted, but the polarization doesn't change. But if I have my half-wave plate, you know, and I orient the axes at the right angles here and stuff, the light that goes through the half-wave plate, the polarization will be rotated 90 degrees. Okay. So what was S here, you know, or what I call S there being vertical. What was vertical there? Oh, come on. What was going to be horizontal here? What was horizontal there was vertical there. So that seems like, and we have all these polarization techniques for doing phase shifting if the test and reference beams have orthogonal polarization. And so this is a nice way to get the test and reference beams to have orthogonal polarization. Okay? So that's pretty nice. Well, I had this dream for, you know, like 20 years or something. I was dreaming about this. And we tried all kinds of ways to make a good pinhole in a half-wave plate. And we failed every time. But then technology came along, and the focused ion beam instrument became available, and now you could drill little holes into things. So I was so excited here So I had a student who sent off a half-wave plate to a company that had a FIB, focus ion beam machine. And lo and behold, we were able to make wonderful, very, very clean apertures in half-wave plates. And so I was so excited. And so the student here, Mark, Robert M., but went by the name of Mark Neal, did his PhD on this. And this, I don't know, this diagram makes it much more complicated than what it really is. Maybe he was trying to snow the committee, I don't know. But anyway, let's go through it here. So what he had, I mean, a million ways of doing phase shifting once if you can make the test and reference beams have orthogonal polarizations. And we've looked at millions of ways. But what he did for his dissertation was what he had to use was an electro-optic modulator that introduced a phase difference between the two states of polarization, the S and the P. So anyway, he had a laser, and then some polarization, and I mean half-wave plate. The whole thing is we have light instant on this EO modulator with a polarization at linear polarization at 45 degrees. So we can break that into a horizontal component and a vertical component. And so all that goes through the system here. This is what he's testing. And it's focused here on his PDI, so the half-wave plate with a little pinhole in it. And so, you know, the reference beam is not changed. State of polarization is not changed, and while the test beam is. And so he could then put in an analyzer to pick out, say, the vertical components here. And he could introduce a phase difference between these two by using the EO modulator. And so that was the interferometer. So the whole trick is to have a good half-wave plate with a small pinhole in it, which you can do with a focused ion beam. Any questions on that? The next is a technique that was developed by a woman by the name of Carolyn Mercer. She came here and did her PhD working for Kathy Kreth. And what Carolyn did was she had a liquid crystal here. And by applying a voltage to that liquid crystal, she could change the optical thickness of the liquid crystal. And then inside this little liquid crystal, she had put a little plastic microsphere inside here. And so now that would act as our diffracting element. That would give us our spherical wave. And test would go around that. And by applying the voltage, she could change the phase of the test, but it would not change the phase of the light diffracted by that little microsphere. And so that worked pretty well, and this is some results that she got using 5 phase-shifted frames, just simply by changing the voltage going to the liquid crystal. Okay. That worked pretty well. Another technique that I saw, I guess it was in SPI newsroom a few years ago, is some people in Italy took a lithium niobate crystal and they etched a little hole, I guess, in it here. And by applying a voltage to the lithium niobate, they could change the optical thickness of it. But for the pinhole, of course, they're not changing anything, and so they would be changing the phase of the test beam relative to the reference beam. So another way. So you see, you're getting the idea. There's for years we were kind of thinking, how do we really do phase shifting for a PDI? And now there's millions of ways of doing it. So here's another way here. This is one that we have played around with quite a lot out at 4D. And so again, we talked before about our little pixelated polarizer array we put in front of the detector. And to make that work, you just have to have the test and reference beams to have circular polarization of opposite sense. And so again, we just want to get the two test and reference beams to have orthogonal polarization. And so the idea here is the following. I'll show it in the next picture maybe best. We're going to make, well, what I'd like to do, what I've been dreaming about doing but haven't been able to do yet, is to get a wire grid polarizer where the wire grids are, say, vertical here, but for a little circular region in here, a micron or so in diameter, a couple microns maybe in diameter, it will have the wire grids going horizontally. And so the polarization that gets through here is, orthogonal, well, between these two regions is going to be orthogonal. And so that would give me my test and reference beams having orthogonal polarization. So, I've been dreaming about this for a few years, and I still haven't been able to buy one of these things or to make one of these things. Anyone have any ideas where I can get one? Or can anyone make one of these for me? I've been dreaming about it. I mean, just like the hole in the half-wave plate, I dreamed about that for 20 years, and then suddenly it was possible to do. I figure if I dream about this for a few years, then suddenly it's going to be possible to do, okay? Yes?
It's going to work as printed conducting material, or does it have to be physical wires? I mean,
No, it could be printed conductive material. Can you make one for me?
I can't personally.
No, if you can find someone who, here we go. The what? Okay. I mean, these are really fine. These are nanometers apart. What? No, yeah. I want it to work. Maybe we could make one that works in at 10 microns, because they don't have to be so fine. That would be interesting to do. I don't know. If someone can make one of these, I won't make you take the final exam. So. Anyway, so I don't know how to do this yet, but I mean, I'm sure it's going to happen. But there are ways to invent your way around this. And so, but I mean, I prefer this. This is what I really want. And hopefully before I die, I'll have one of these. But since I don't have one now, this is what we're going to make something like this. That works a little bit like this. Maybe not quite as elegant as this, but it will work. So first off, I mean, I can buy these wire grid polarizers. That's no problem. I mean, we use them all the time at 4D. We make our mask for our phase shifting interferometers. And I can drill a hole in here using my focused ion beam, since we've been able to do that for 10 years or more. So that's great. So what I'm going to do is the following. I'm going to, instead of, I mean, this is what I want. Don't know how to do it. So this is what we're going to do. We're going to take a substrate here. So just a thin substrate of probably glass. And on one side, we're going to put a polarizer, and I'll say X. Okay. On the other side, I'm going to put a polarizer, let's say Y. So these are orthogonal. And with my focused ion beam machine, I'm going to drill a hole in here, 2-3 microns in diameter. Now, so now the light coming out here will have this state of polarization, and the light coming out here will have an orthogonal state of polarization. Now this is crossed relative to there, so I don't get much light through. So what I'll do, I'll put another layer in here with a polarizer at some other angle. I say 45 degrees, but maybe it's 20 degrees or something. Anyway, some other angle. And then I'll put the Y polarizer on the outside. And so some of this light will now get out of here. And by changing having different angles for this inner polarizer here, I can get different amounts of light out here. So anyway, now the light that goes through here will have one state of polarization. So the reference beam will have one state of polarization. And the test beam is going to have the orthogonal state of polarization. And so I can do all my tricks here that we have talked about when we talked about phase shifting. So, you know, we have made these, and they actually work pretty well. I mean, it's not nearly as elegant as this, but it actually works pretty well, and this is just showing some results for it. Okay. So that's you know, lots of ways of phase shifting PDIs. Maybe you can invent some more. If you do invent more, let me know about it, so I can add more slides here of different ways to phase shift PDIs. And the PDI, you know, it's not used a lot, but it's used some. And I mean, the nice thing about it, you don't have to, you know, bring around a reference beam or something like you have to do in a Twyman green. And you just have a light coming to focus, and you put your little interferometer there, and that's it. And you don't have real serious vibration problems, because it's kind of a common path type interferometer again. It doesn't have to be perfectly monochromatic. It's just it's a pretty cool and useful interferometer. The main problem being as you change the tilt, the fringe contrast changes. But if you're going to phase shifting, yeah, I mean, there's no reason to introduce tilt. And so, I mean, it works very, very fine phase shifting. This little device here is actually very, very, very useful. Okay, now I want to go, so that's the end of the PDI, but I'm now going to talk about something that is very close to a PDI. In fact, think of it the same way. And this is something that was invented by a man by the name of Gary Sommargren. And Gary he was a great interferometry guy. And he generally, most of the interferometry work he did had some, he was doing something with polarized light. And he unfortunately died at a fairly young age, but he did a lot of work during his short life. So we'll call this a Sommargren diffraction interferometer. And a little bit of this at the beginning is kind of what we saw earlier when we talked about short coherence length sources and interferometry, but I'll go through it here. So we have some source here that has a short coherence length. And here we have his polarization interferometer. And so light will go down here, here, and back. And he used a little 90-degree prism here, I guess, to send the light back and displace it sideways a little bit. And what was reflected the first time and wanted transmitted second, so he puts in his quarter wave plates here like we've seen before. And so he has one beam here and another beam coming down here and out. So these two beams coming out, initially they have orthogonal polarization, and then he puts in a polarizer here, so what comes through this lens will be one state of polarization. And then he was going to do phase shifting by moving this mirror back and forth. So this mirror down here is mounted on a PZT. And so the whole purpose here is just like what we saw before. He's going to change, you're going to have two beams coming out of here, and there's a path delay between the two beams. Okay? And he can vary what that path delay is simply by moving this corner cube or 90-degree prism, whatever it is, probably, let's say a corner cube. Okay, so now light comes out here, and he focused the light down on an optical fiber. Okay, and the fiber goes here. Now, this is the mirror he wants to test. The fiber is pretty small, and the light coming out of that comes out over a fairly large angle. So some of the light's going to go straight down here to his CCD camera, and some of the light is going to go up here to his optics under test. Anyway, the fiber is small and it cleans up the beam. That's a little bit like a PDI, but anyway. So we have a nice spherical wave coming out of here, going both here and here. Now the light going up to the mirror under test is going to come back here. And this fiber, the end of the fiber, is at the focus, or is at the center of curvature of this mirror he's testing. So light will go back here. And I'll come back to this diagram in a second. I want to show what happens. So light goes back there. So here's our little fiber. And a little semi-transparent metallic coating on the end here. So light went up to this mirror, and it comes back on itself, focused here, and it reflects off here. Boy, what am I doing here? It reflects off here, and it comes down here to where our imaging lens is. So the light went up here, comes back here, reflects off there, and comes here. But the light that originally came out of here, some of it came down here, too. So that was the reference. This is the test. Now there's quite a path difference between the two. And as a short coherence length source, so he matches the path, for here and what went straight here simply by moving this mirror back and forth. So it's true, he has both beams coming here and both beams coming here. And it's only one of those beams that he's going to match the paths for. And so just like in the interferometer we discussed a few weeks ago, we're going to have reduced fringe contrast here because we have a beam that's incoherent. You have both the short path here and long path here going both here and up here. And only the short path one going here and the long path one going here will interfere. But the beauty of this, or what he really liked about it is, oops, if I get it right here. If the beauty here is that he doesn't really have a reference beam. He's relying on the end of this fiber being flat. And the light's focused down here, so it's not using much of that anyway. And so he's getting around the problem of having a high quality reference here. And everything is, cleaned up by the fiber. And he can do phase shifting by moving this. There are other ways he could do phase shifting, but his technique was to move this mirror back and forth. Any questions on that?
I have a question. What if you don't have a nice focus coming back, like the next slide? So the fiber is really thin and you need a very nice...
We're saying this end here has to be good quality. Has to be flat.
What's the size of it?
We're talking about a few microns here, really. So this is not for testing a lousy mirror that produces a large spot back here. This is for testing a high quality mirror. And he actually made this for lithographic, testing optics used in lithography. And he wanted, I mean, if you had a lousy mirror to begin with, you don't need to worry so much about the reference beam. So this was really intended for testing very high quality mirrors.
And nearly spherical.
And spherical, yeah, nearly spherical. Not aspheres, but spherical.
Could you make it work with an aspheric surface by having CGH in front of?
Yeah, we haven't talked about CGHs yet, but you could. I mean, a lot of ways, we'll talk about many ways of using computer-generated holograms later, but I mean, I should have said this at the beginning. His whole purpose here for doing this was to produce very high-quality spherical surfaces, and he was worried about generating a reference of high enough quality. And so it's pretty restrictive what he wanted to use this for. But for producing high quality, for testing high quality spherical surfaces, this is a very good way. And it's not widely used, but it's been used by Livermore and a few companies, but not a lot. Boys thought it was pretty cute, and I don't think he ever published this anyplace other than he gave a talk on it at a meeting, and that's where I got this slide from. Okay, I'll understand it. So two neat things. One is a way of using short coherence length source, because he was worried about all the spurious fringes you get if you have a long coherence length source. So this was a way of cleaning that up by using a short coherence length source. And then it was a way of really avoiding the requirements on a reference. The only real requirement was that over a small region here, microns, this had to be a flat surface. And the fiber itself was cleaning up the beam, giving us a nice spherical wave.
Is that accomplished by normal fiber cleaving?
Yeah, I don't think he did anything, as far as I know, he didn't have to do anything, any fine polishing or anything, but I'm not sure. I'm not sure. We're using such a small region here. No, microns is all. Any other questions? Okay. Different topic. Testing cylinder lenses. This is always never very easy, I guess I'd have to say. So we're going to look at two different ways of doing this. We're going to look at using a cylindrical lens, Null lens, transmission cylinder optic, and we're going to look at using a special diffraction grating. And I'm going to claim that the diffraction grating is a better way of doing it. So here's a lens that is a cylinder. And here's my Fizeau. And just like, when we were testing spherical optics, you could, in your Fizeau, you make it so you make the diverger lens here, or transmission sphere, they generally call it, so that the last surface is a spherical surface, and the beam leaving here is normal to this last surface. So you get a beam retro-reflected back, and that becomes your reference beam. And then here's the mirror you're testing. Well, we can do the same thing that we do for spheres, we can do it for cylinders, where now this lens here is designed and fabricated not to produce a spherical wave, but to produce a cylindrical wavefront. So we would have a line focus right there. And so this would be made, so the last element here is a cylinder, and the beam leaving here is normal to this last element. And we go out here, line focus, and here's our cylinder we're testing, and we'd put it at, so the center of curvature of the cylinder is where the line focus is, and the light would come back and you would interfere the two beams. Now this is a little harder than testing a sphere because you have to, now it's angle critical because it's a cylinder. And so not only do you have to position it right location longitudinally, but you have to rotate it to the right angle. And so people have tested optics this way, and you can get a nice plane wave coming back here, both from the reference and from the test. The main problem with this approach is, being James C. Wyant, where C stands for cheap, I really don't like this at all, because you end up spending more for this than you spend for your car. And it's a very expensive element if you want a high quality one. But people used to use this technique, and maybe some people still do, I don't know, but I don't think it's used too much anymore. The better approach is the following here. So again, I'm just going to use a Fizeau. It could be a Twyman green, but I use a Fizeau. And our transmission flat here, so this is our reference. And we come in here, and we're going to put a diffraction grating here that is going to have straight lines, but it's going to have a spacing that is just right for producing a spherical wavefront. And so the beam, you'll have different diffraction orders, but this is generally a reflection grating, but it doesn't have to be. But normally, for testing a mirror here, it would be a reflection grating. That produces a cylindrical wavefront in the first order. So I have my line focus here. And here's my cylinder. So again, center curvature is where the line focus is. And again, the angular position of this is going to be critical, because this is a cylinder. It's not rotationally symmetric. And so the light will go back here, come to focus, be diffracted off here a second time, and produce a nice plane wave. So this has become kind of the way of testing cylinder surfaces because you can make fairly easily these gratings, and you can buy them then for a reasonable price. Now, when this first began being used, most of these gratings were ruled gratings. And ruling engines had been developed so well over the years that you could really produce nice straight lines, and you can control the spacing to nanometers. Or at least, fractions of waves. But over the years, the ruled grating has been replaced here with electron beam recorders for producing these cylindrical gratings. And you mentioned computer-generated holograms a little while ago, and we'll talk a lot about computer-generated holograms in a chapter where we talk about testing of A-spheres. But these are just made, the line spacing is calculated fairly easily, and the electron beam recorders are used to write these lines in photoresist, and then the photoresist is processed to produce our grating here. And so for $2,000, $3,000, $4,000, you can get quite good gratings for testing cylinder optics. Okay, any questions? Yes?
Is this grating something similar to the zone plate except like stretch out?
Yeah, the zone plate, if you calculate the positions of the lines making up the zone plate, that spacing is the same as what you would have for these lines here. So this is a a one-dimensional zone plate, I guess I would say. Okay. Next topic. And I think, I'm not sure, but I think this is where if we go back to our original schedule, I think this is where we're supposed to be at the end of the class. So we're pretty much on schedule. But I have 10 minutes left, so I can get a little bit ahead of schedule. So this is on long wavelength interferometry. And I'm going to talk about two different wavelengths here. One will be 106 microns, and the other one is 10.6 microns. And you could add a lot of other wavelengths as well. The main point of this section here is just say, you know, we're so used to doing interferometric testing using visible light, but I mean, you can use long wavelength light, you could use UV light. It doesn't matter. I mean, it's more difficult when you can't see the light, but it's not that difficult. You still can do it pretty nicely. So the two wavelengths I'm just going to mention in this section here, one is 106, and so that's a little bit reduced sensitivity. Sometimes you're doing a test and the visible light just is a little too sensitive for you. And so maybe you want to go to a little shorter wavelength. But maybe more often you want to go to a much longer wavelength. And there are probably at least 3 reasons why you like to use 10.6. I mean, here you have greatly reduced sensitivity, since the sensitivity would be inversely proportional to the wavelength. We're reducing the sensitivity from visible light. If we go from visible light to 10.6 microns, we're reducing the sensitivity by a factor of, I don't know, 16 or so. So sometimes that's useful. We can test infrared transmitting optics. I mean, there's a lot of optics made to work out in the infrared for night vision purposes. And you always like to test the optics at a wavelength close to what it's being used at. So this turns out to be pretty useful. And then the last item, which is why I really got interested in this a number of years ago, was for testing optically rough surfaces. So you're making some optics, and so you start out grinding the optics. And grinding is much faster than polishing, so you like to do as much work grinding as you can. And so you like to be able to test these surfaces when when you have a ground surface. And so by going to a long wavelength, you can do that. We'll show that. Well, I don't know. I mean, there are a lot of different sources nowadays for these wavelengths. And slide which I made up a number of years ago, I just said, well, diode pump YAG laser is a good source. You know, you have excellent coherence properties. But there are lots of sources here you can use now. And, you know, pretty much normal optics will work, and pretty much a normal CCD will work. Sensitivity is reduced, but you generally have so much light, it's fine. And all the conventional interferometry techniques we've talked about, you know, you can make phase shifting here, you can do PDIs here, you can do scatterplate interferometers here, everything. At 10.6 microns, I mean, a CO2 laser is just superb. It has wonderful coherence properties. For the materials here, you generally use zinc selenide or germanium. And you used to use pyroelectric Vidicons for detectors. Nowadays you have bolometers, solid-state bolometers that you would use. And you have, I mean, all the conventional interferometry techniques work well. So this is looking at, I mean, this was a terrible piece of optic here. It was a diamond turn mirror. The mirror was for some reason in the shape of a triangle. And I mean, it's a terrible mirror. And if you test it at 0.633 microns, I mean, you have so many fringes, it's terrible. But just to show the great reduced sensitivity going to 10.6 microns, this was testing the same mirror at 10.6. Everything looks good at 10.6. Even once I tested a 2x4, a wooden 2x4, worked well. I mean, I don't think there's much business in interferometrically testing wooden 2x4s, but it worked. Okay. Well, actually, I think I'm going to stop here. The next topic I'm going to get to, which I don't have enough time to cover today, but it's a topic that was very near and dear to me, was testing optically rough surfaces. So what we will do the next class, next Tuesday morning, bright and early, we'll come back here and we're going to talk about testing of ground surfaces and show how well that works. So any questions before we break?